Okay, so yesterday we stopped at the discussion about RS232. Okay, I have explained how RS232 comes into the application, especially into the industry and consumers. Hang on, but attention. All right. So let us continue the details about RS232. Okay. I'm trying to hang on. Trying to set. Okay. Right. Yeah. Can you see the? Can you see my screen? All right. Good. So just let me set this over. Okay. Okay. So let's discuss the detail about RS232. Okay. So one of the requirement of RS232, the connection between, hang on, I'm trying to find my, okay. So the idea in RS232 is you want, okay, to connect, okay, a device or so-called as a transmitter to a receiver. Okay. So technically, the channel between transmitter and receiver is wired using wire. Okay, wire. And the requirement is that the connection must be less than 50 feet. Okay, less than 50 feet. Cannot be longer than 50 feet. And please correct in your notes the data represented by voltage level is around, actually the level is around 12 to negative 12 volts, not 15 volt, 15 to and negative 15 volts as stated in your current slide. Okay, but these are the typical value. So we will look into the actual practical value later in the next slides. Okay, and the common number of pin for RS32 can be 25 or can be 9. Okay, This is and also in RS2 specified transmission of character. There's a it sends data in the form of ASCII codes. ASCII codes. Okay. So basically, it sends a stream of data. Okay, it means stream of data through the channel. Okay, through the channel in between the transmitter and receiver, and then the data is translated. Okay, the stream of bit is translated using ASCII code. Okay, and the transmitter never leave wire at 0 volt when idle. Okay, means that it put negative. Okay, negative level, constant negative level. Okay, if it is in idle mode, it will send a negative. Okay, let's say 12 volt on the channel. Okay, the voltage level on the data transfer, the voltage it will send constant negative 12 volt over the channel or on the wire, right? So these are the pin layout for RS232 for 25, okay, 25 pins, and for 9 pins, okay. So basically they put a number for male, the one that have pins pointing out, okay, on the port, while female the connector basically consists of holes that match with the male connector. So the numbering, okay, for male is from 1 from top left, okay, clockwise 2, 3, 4, 5, 6, and then stop at 5, okay, and then 6, 7, 8, 9, okay. Okay. So that is just a technical part of the RS232 connector, and this is in details the function of every bit of the RS232 pin connectors. Okay, but let's focus on the 9 channels, so 9 pins. Okay, basically they are number 1, they are data carrier, detect, receiver data, transmitter data, terminal ready, signal ground, data set ready, request to send, clear to send, and ring indicator. But in the practical application, we don't usually use all number of pins. There are only a few important pins that are utilized in a certain application of RS232. Okay. Okay. So how to identify the asynchronous character? Remember that this RS232 is asynchronous because the data it sends, okay, the data sends 1 bit per bit, and so it takes some time for the data to be translated or converted by the receiver. Okay, so in other words, it is some form of non-real-time communication system. Okay, data or data transfer. So the transmitter indicates start of next character by transmitting a 0 bit. 0 bit. Okay, 0 bit means this is the the layout of the data. Okay, in a block, in the form of block. Okay, basically when the receiver reads 0 value, okay, 0 value, okay, it will start to do a conversion. So zero value, okay, means that, okay, means that when it receive a low voltage level on the transmission on the data transmission line. Okay, let me. Okay. Okay. So it will, sorry. Mm, zero, sorry, not low, high. Zero. Zero is represented by high voltage level. Okay, typically 12 volts. Okay, 12 volts. So it will, when it receive, when the transmission detect a high voltage level, okay, this is represented by 0 bit. Okay. Okay, so the receiver can detect transition as a start of character. What does it mean? It means that this okay, represent the 0 bit, okay, for the 0 bit value for the start bit, okay, but in the form of voltage level. So the receiver will start to do conversion when it detects the falling edge, okay, this falling edge. Okay, when it detect, okay, after it detect the falling edge, okay, of the start bit 0, okay, after that, okay, the receiver will do the conversion, okay, and the data, okay, is sent in a bit stream, okay, okay, and also it is sent in reverse order of significance, okay. This is the first, okay, the bit sent on the transmission, but it represents the least significant bit, okay, and so on, okay. And the transmitter must leave wire idle. Okay, wire idle, like I have explained before, idle means that when it's in the standby mode, okay, when it's standby mode, okay, the transmission line, the transmit, okay, the data transmission line, okay, the voltage level will be a constant, okay, constant negative value, okay, constant negative value, okay, 12 volts, constant, okay, until, okay, we restart the conversion by changing the voltage level to high, okay. But when it is on in constant, it will send the voltage level will be set at negative value, okay. So a character can be represented by 7-bit data, okay, 7-bit data, okay. If 7-bit data means that you sending a 0 to 0 bit to 6 bit, okay, bit 0 to bit 6, okay, can be up to 8, okay. And transmitter send 1 after each character. After each character means that is what is called, this is basically 1 after the, here, after the stop bit, okay. So let's say in details example of the data, okay, transmission on transmitted on the RS232, okay, between the transmitter and receiver, okay. We have a transmitter, Okay. From the transmitter to receiver. Okay. So the RS2 will be idle. Okay, the state of idle, it sends a negative 12 volt, okay, for a long period of time, and then when it's ready, the receiver will be notified or ready to do a conversion when it detect start bit. So start bit mean the voltage level change from negative 12 volt to positive 12 volt. And after it detect this falling edge, okay, only falling edge, so the data will be start to be transmitted. Okay, so this will be the least significant bit, and this will be the most significant bit. Okay, in this case, there are how many 8 bits sent. So this bit, okay, is actually this bit. Okay, and this bit is this bit. Okay, and then this is the stream, the bit stream sent over the transmission. Okay, the transmission line. Okay, and the system will stop after you receive a negative voltage or 1 bit value as a stop bit. And also there is another important concept. Okay, it's called as parity. Okay, parity. We will discuss about parity in details. So what does mean parity? Parity, okay, is a way how to check error on the transmission line. Okay, in this example, the parity bit is not, okay, is not specified, okay, on the data set. Okay, it usually comes after the data bits, okay, and come after the data bit. But in this case, it's not specified. Okay, this parity, we set the rule. This is a rule. Okay. So in your notes, it must be maybe slightly different, but it's okay. I will explain. So basically, what is parity? So parity, so basically, it is a concept to detect errors. Okay. So basically, scientists, okay, and engineers, okay, trying to figure out how to make sure the data that we send is valid. Okay. So what is actually it is actually a single bit error is detected by a bit, and this bit is called parity bit. Okay. Okay, so how we do that? So I give you a simple example. So we have a transmitter. Okay, so we send the data through a receiver. Okay. Okay, over a channel. Okay. So basically, okay, let's say we send 4 bit stream. Okay. Okay, 4-bit stream. Okay. Then we can set the parity bit rules. Okay, parity bit rules. For example, there are 2 types of parity bit rules. Okay. Uh, So they are odd and also they are even. Okay, even parity bit rules. Okay, let's say for an example we send, okay, a 4-bit stream, let's say 1 0 1 0. Okay, so 1 0 1 0. So we send 1 0 0 1 0 to from the transmitter to the receiver. Okay, and then we set the, let's say we choose odd parity rules. Okay, odd parity rules. So if, okay, let's say odd, we choose, let's say odd. Okay, from this is the bit stream that we want to send, and then let's say we set the odd rules. So if we add, if we use the odd rules, so the one bit that must be added, okay, when we sum up the bit, all the bit in the stream, including the parity bit, the number or number of one bit must be odd. Okay, you get. For example, if we set odd, okay, so the data that we should transmit from the receiver, including the parity bit, it should be 1. Okay, okay, it should be 1. It should be, because, okay, if we set odd, the number of one bit should be in odd number. Okay, odd number. So in this case 1 2 3. Okay, so we send from transmitter to the receiver. So when we got the data, or we read the data from the receiver, and then the rule that we set is odd. Okay, so to verify the data, when we sum up the number of one bit, it should be odd. Okay, okay, if, okay, remember this is the original, okay, the original data we send from the transmitter to the receiver, including the parity bit. If we set F even, okay, so the data that we send, okay, from the transmitter, including the parity bit value, it should be 1 0 1 0 0. Okay, okay, are you following so far? Okay, so if we use the even parity rules, so the total number of 1, including the parity bit, it should be even number. Okay, so how does it work? Okay, how does it work? So this is our channel. Okay, in RX232 transmission, this is our channel. There are many factors that affecting our data. Okay, affecting our the data bit stream. There could be noise. Okay, there will be noise. Remember that we are sending data in the form of bit value, which is in an energy form of negative or positive voltage. Okay, there could be noise. Okay, let's say let's say this is the bit. Okay, the bit actual bit data that we send. Okay, this is from the transmitter. Okay, transmitter. Okay, and this is the bit, and then we set the odd rules. Okay, and this is what actually should be received by the receiver. Okay, if we set even, this is the data should be sent by the received by the receiver. But in some cases, okay, because of the noise, okay, there could be noise, and this, let's say this bit, okay, because of noise, okay, Okay, I've use a different color because of noise. Okay, all then suddenly this become one. Okay, so due to noise. Okay, noise. N-O-I-S-E. Due to noise. Okay, the first bit that we read, or the transmitter read, is become one due to the noise. Okay, due to the noise. Noise can be electrical noise. Okay. Okay. Then we will discuss in detail about noise in the later chapter. So how do we check? So because let's say in the beginning, okay, we set the parity rules as odd. Okay, and this is what we get from the receiver. This is the original data, the bit stream. So when we calculate or we sum up the number of bit, okay, so the bit become 1, 2, 3, 4. Okay, so it does not comply with the rules that we set at the beginning. So so the system, okay, or the receiver can detect the data is invalid. Okay, similar to the case if we set to even, okay, due to the noise, this data, okay, become 1. So when we calculate the total number of 1, okay, the total of number of 1 in the data bit including the parity bit, so the number of 1 become 1, 2, 3. So it does not comply with the even. Okay, so so in this case the data is invalid. Okay, invalid. All right. Okay, let test your understanding. Okay, look at this example. Okay, look at this example. Okay, this is the start bit. Okay, and this is the parity bit, and this is the stop bit. Okay, now let's see. Okay, let's so will become the least significant bit. Okay, and this will become the most significant bit. No. Yes. Okay, this is the most significant bit, and this is the parity bit. Okay, it's the parity bit, and in this case, okay, it's set as even parity. Okay, 0. If the parity bit value is 0, so the rules we set this rule as even. Okay, even. Okay, even. Okay, and this is stop bit. So the question is the data valid? Okay, so let us first figure out the data value. Okay, so the data value will be 1, 0, 1, 1, 0, 0, 1. Okay, so this is the bit stream or the data. Okay, and then the parity bit is value, the parity bit value is 0. And then the rules that we set is even. So if we set the rules as even, okay, then the total number of 1 bit should be even. So in this case, how many 1 value? 1, 2, 3, 4. So there are 4 1 bits. So it is even. So we can say the data is valid. Okay, so that is the rules. So that's one example. Okay. Okay, let us look at the second example. Okay. Second example. RS232 signal in figure 1 is sent with 8 data bit. And you see the rule is odd parity. Odd parity. Okay, so this is the start bit. Okay, because after the falling edge. Okay, hang on. Sorry. Okay, so be careful in this example. Okay, in this example, if you look at this example, okay, this is not voltage level. This is logic. Okay, you see, this is logic. Logic 1 and logic 0. Okay, logic 1 and logic 0. So the start bit, see, so the start bit should be, okay, the start bit should be 0. Okay, start bit should be 0. So this is the start bit. Which is 0. Okay. Okay. So after the start bit, this will be this significant bit B0, B1, B2, B3, B4, B5, B6, B7. Okay, and this should be the parity. Okay? The parity bit. Parity bit. Okay. So we have to figure out what is the value of the data. So B0, B1, B2, B3, B4, B5, B6, and B7. And this is the parity bit. Say the parity bit. So the data value will be 1, 0, 0, 1, 1, 0, 0, 0. And the parity bit is 1. Okay. And so this is the data. Okay. And let's check whether the data is valid or not valid. So if you count, in this case, okay, the rule that we set at the beginning is odd parity. Okay, so we need to figure out how many number of 1. Okay, so in this case 1, 2, 3, 4. So 4. 4 is even. Okay, 4 is even. So that is against the rule that we set as the odd parity. So in conclusion, so this is that the data is invalid. Right? The data is invalid. Okay. So if you have any question, you can ask. Okay. Okay, timing, so the data must be sent, okay, so that the conversion, there will be no error in the conversion. So basically the timing is controlled by a clock, okay, by a clock, okay, by a clock, okay. So the transmitter and the receiver has their own clock, but the transmitter and the receiver must, okay, synchronize the clock between them, between the device, and the timing is measured in bit per second, or BPS, bit per second. Okay, it detects detection of start bit indicate to receiver when subsequent bit will arrive, as I explained before. So the hardware can usually be configured to select matching bit rate by using a switch setting software, okay, or auto detection. So means using an extra circuit, but you don't have to worry about that. We're not going to discuss in details. Okay, and basically baud rate measure the number of bit changes per second. Okay, so in RS-232, the common rate of the transmission rate is 9,600 BPS, 14,400 BPS, 90,200 BPS. Those are the common BPS rate. I think if you do Arduino programming, you also have to set the bit BPS, or bit per baud rate, or the bit per second, okay, rate, before you can do programming, okay, from your PC to your Arduino. Okay, so basically the BPS measure number of bit transmitted per second. Okay, BPS. Each signal change represent one bit. Okay, so baud rate and bits per second are equal. So meaning that, let's say for 900, 600 bit per second, okay, so that means one bit transmission time is 1/9 transmission time in second, 1/9600, or equals to 10.41 millisecond. Okay, millisecond. Okay, that's the time in second for one bit transmission. Okay, framing is also important. So start and stop bit represent framing for each character. Okay. So the framing means that the BPS, or bit, but the baud rate of the transmitter and receiver must match. If they don't match, so there will be error. Okay, and this problem is called framing error. Okay, so in the serial communication can be half or full duplex. Okay, full duplex means that the device, okay, full duplex means the device and receiver, they can talk and listen at the same time. Okay, okay, that is what I mean as full duplex. Okay, full duplex. But half duplex means that the device cannot send and receive at the same time. So they have to alternate role. Okay, so we have two devices for half duplex. device 1 must be, when it talks, device 2 must listen. Okay. And then you can change role during half duplex. For example, device 2 become the transmitter or talk, then device 1 must listen, or it must receive the data, okay, the information. Okay, so that is the concept of half duplex and full duplex. So half duplex, basically minimum it needs 2 wires. Okay, for half duplex. For full duplex, minimum 3 wires. Okay. Okay, this is a simple, okay, representation of serial communication. So simple, A and B, A just send to B. Okay, means that this is a permanent role, okay, for simplex. So this become the transmitter, okay, transmitter, okay, and this become the receiver. Okay, or this become the talker, this become the listener. Okay. Half duplex, okay, data can only travel one direction at a time. A send to B, and when that transmission is finished, then B can send to A. So half duplex. Okay, full duplex, okay, no problem. They both can talk, both and listen at the same time. So that is full duplex. Okay. So the comparison. So the direct basic is unidirectional, only one directional, that cannot change. Half duplex, 2 directional, and full duplex, 2 directional simultaneously. So half duplex at one time. Okay. So send and receive, I think you can read. Okay, performance, this is the least performance because the transmitter cannot verify. Okay, whatever have been sent to the receiver, that's it. Okay, so most likely the transmitter will okay, don't bother to check what is happening on the receiver end. Okay, half duplex, okay, there is a two-way communication, okay, but there is a time constraint. I mean the time for the data to be replied or verified will require some more time. Okay, but the full duplex is the most performing mode. Okay, example like simplex is keyboard and monitor. Okay, so monitor will not talk back to your keyboard lah. Okay, except for the very advanced keyboard. Okay, that has a user feedback. So that's different. Okay, half duplex is walkie-talkie. Walkie-talkie, you have to press. You have a button, you have to press. Okay, and then you have to release. Okay, press you want to talk, and then release you listen. So in one set of communication of walkie-talkie, if we have many listeners or many walkie-talkie involved, only one can talk at one time. Okay, full duplex is a telephone, like a telephone. That's a simplest example of full duplex. Okay, this is the limitation of hardware. Okay, the effect of wire. We want to send, okay, a nice square edge. Okay, that's ideal. But due to the interference, okay, due to the resistance, okay, on the transmission line, okay, the signal basically will be distorted. Okay, there will be, okay, noise, okay, due to the noise, okay, or resistance. Okay, so that's why we need to avoid using a very long wire. Okay, because if you have long wire, so there's a higher possibility for noise to come into the system. Okay. So the RS-232, they specify how precise a waveform must generate. Okay, so it specify the, you know, they will specify the rate. Okay, so in RS-232, basically logic 1, the range will be from -3 volt to -25 volts. Okay, but we have seen the typical level is 12 volts for logic 1. Okay, as for logic 0, so logic 0, the range is from 3 volts, negative 3 volts, okay, to 25 volts. But the typical level is 12 volts for logic 0. Okay, logic 0 or bit value 0. Okay, so I think that's finished about RS-232. We carry on with GPIB IEEE 488. Okay, GPIB stand for General Purpose Interface Bus. Okay, this is basically an industrial-based interface for communication between instruments from different sources. I mean, manufacturer. Okay, different manufacturer. Okay, so this protocol. Okay, how to use the protocol? Okay, the codes or the firmware is publicly available. Okay, so a manufacturer, okay, company that produce instruments, okay, like for example HP, okay, like other big company that produce instrument, okay, other company that can use this code to as a communication device between instrument. Okay, it's an industrial based standard. Okay, the advantage of GPIB, okay, can be listed as follow. Okay, so it's a simple hardware interface. Okay, and easy to connect multiple device to a single host. Okay, there will be a one controller. Okay, in the GPIB there is one controller. Okay, that controller will decide, okay, the device, which device will be the talker and which device will be the listener, or we will decide which device will connect to other devices. Okay, and the good thing advantage, device, it has a different specification in terms of the speed. Okay, so GPIB allows the mixing of slow and fast devices. Okay, and this is well established. Okay, and it has a very strong connector. Okay, the connector, okay, strong connector, and then it can be mounted on the back of the equipment. Okay, using which you can which you can mount, and then you can secure the connection using the screw. Okay. So it cannot be easily be removed, like fire wire or USB. So you need to unscrew. Okay, there's a screw you have to unscrew before you can pull out the cable. Okay, but there are some advantages. the connectors or the cable are basically bulky or mechanically bulky. Okay, and then the cost is much more expensive than a normal, than a usual connector or interface standard like RS-22, 232, USB, and so on. Okay, and then it's a little bit it's not easily available in the store, so you have to purchase from a specific supplier. Okay, but and also in terms of the implementation, there could be some interchangeability issue. For example, some device they use a different communication, or I mean the standard for communication for certain device should be different, and then they need to convert, and then they need to adapt with IEEE 488. Okay, so it was developed in 1975. Okay, I mean developed in 1970, and then after few process of discussion, it has been standardized in 1975. Okay, so basically the first company that popularized the use of IEEE is National Instrument. Okay. The data rate is 8 megabyte per second. It's quite fast. Okay. But so if we have more sharing, okay, sharing in the bus line, so basically the data rate will be divided by the number of device. Okay, by the number of device. But considering the number, okay, considering the rate, that the data rate is still okay. You can put a lot of equipment. Okay, but it is very not wise if you put too much device stacking in one application or in one system. So you have to limit the number of device connected in one system. Okay, these are the specification. Okay, the data signal. Basically, the width is 8. Okay, and then the bandwidth of the speed about 1 megabyte per second, but later is extended to 8 megabyte per second. It uses the parallel. You can see the number. There are basically 24 pins, okay, on the GPIB bus. Okay, and then the connector type. Okay, this is the type of the connector. Okay, this is connector. So the maximum length is about 20 meter. 20 meter. That is I'm not sure in foot. Okay, but 20 meter is quite far. And in one time, it can support 15 instruments. Okay, 15 instruments can be connected on the bus. Okay, but the interconnection length between instruments is limited to 2 meters. Okay. So application of GPIB, this is the use in power conversion company. Okay, where it uses IEEE communication to connect between the system and PC. Okay, and it provides ground power to space shuttle load before the shuttle to go off into the atmosphere. Okay, so this is the GPIB description. Okay, there will be one controller, and the other device will be marked as talker or listener. Okay. So device, talker or listener depend on the controller. So the controller will decide which device will be talker and which device will be receiver. Okay, so there will be 8 data bits. So there will be a data bus, okay, a data bus with 8 data bits. Okay, so for DI01 to DI08. So means that 8 bit will be transmitted at a time simultaneously. 8 bits of data, 8. So the data is not transmitted in the form of stream. So it will transmitted parallel protocol. Okay, 8 bit will be transmitted simultaneously. Okay, so in the handshaking line, so handshaking line is basically is the controller will send this data, okay, DAV bar, NRFD bar, and NDAC bar. Okay, so this is called as the handshake data between the listener and the talker. Okay, so the handshake means that the protocol when what the data is want to be sent. Okay, and the control bus, okay, IFC, ATN, SRQ, REN, and EOI is the data, the control bus signal type. Okay, we will provide the information on the bus. Okay, we will decide which device will be the talker or which one will be the listener. Okay. Okay. So the handshake line. Okay, the handshake line will be the data that coordinate the data transfer. Okay. So the controller, like I said, it determines which device become active, and also which device will be inactive. Okay. Also will which device will be the talker and which device will be the listener. Okay. The talker will only send data to other devices, and then the listener will receive the information from the talker. I think this is not. I want to focus. You need to focus on the handshake line. So this you need to focus. Okay. So this is the how the data be transferred for the handshake line. Okay, the control of the transfer message by among the device and form of the method for acknowledging the transfer of data. Okay, this is basically to control or to coordinate the data process, data conversion sending process. So this this process make sure the byte on the data are sent and received without error. Okay, without error. Okay. So that is the purpose of this handshake line. Okay. And there are 3 types. Okay, 3 types of data signals or data bit in the handshake lines, which NRFD bar, okay, not ready for data. So it means that a listener set this line low. Okay, listener, like for example, this listener will set low when it is not ready for data. Okay, it's not ready for data. Okay, but if we send high, if ready to receive data. Okay, maybe for example, at one point the listener is doing some other task. Okay, and then it sends. Okay, let's say it's not ready to receive any data, so it sends low. So let's say for example, it's doing some conversion or doing any other task. So when it is ready, it will send high. Okay, for data ready, and then the controller will set high. You send data ready to the listener set the data ready on the NRFID. The controller will acknowledge, and then the controller will set the talker to send data. Okay. NDAC bar is not data accepted. So the listener set this line low when it has not received any data. Okay, means that this is to acknowledge the controller it is idling or standby. Okay, standby. Okay. When it accepts data, it releases the NDAC bar and it does not go too high, until all listeners have accepted the data. Okay. DAV bar or data valid, a talker set this line to low, okay, low, when it detects a high on the NRFD bar line. Then the data on this IO are settled and valid. Okay. Okay. So you see the for NRFD bar, okay, is for the list, and DAC bar is for the listener, and DAV bar is for the talker. Okay. This is the time transfer timing. This is the representation of the data in the form of bytes. Okay. Example of DAV and RFID. So if, okay, for example, the NRFID, okay, low, then means that device not ready. Okay. When it's high, NRFID high, device is ready. Okay. And if DAV low is data valid. Okay, next, when NDAC is high, data accepted. Okay, and next, when this NRFID high, this device not ready. For at this point, device is ready for listening. NRFID. Remember that only the AV is for talker. Okay, this is for talker. Talker. This is for listener. And also NDAC for listener. So okay, this is not very important. I mean, want to skip to USB, or this is what is very common that we are using, or the universal serial bus. Okay, so USB allow connection of medium bandwidth peripherals such as keyboard, mouse, tablet, modem, and so on, like your smartphone. Okay, so either connect, especially your PC or your laptop to many other devices. Okay. USB specification, the best or the optimum length of cable is around 5 meters. Okay. And on a USB, sometimes, okay, a USB you can extend, okay, using a port. Okay, you can extend the connection using a port, USB port. And then the number of devices connected to a port is 127. But remember, if you are using a port, okay, USB port, the power the power will be on the line will be sharing with other devices. So it's not very encouraged to use a port, USB port, okay, for very many devices, especially for data transfer. Okay, and the voltage level on the USB is around 5 volt plus minus 5%, and the data rate is about 1.5 megabit, and maximum is around 12 megabit per second. Okay, and this is the, okay, there are basically 4 wire on the USB line. Okay, red is the volt for plus 5 volt, blue, white and green are the USB data plus and USB data minus respectively, and black is the ground. Okay, ground. Right. So I think We continue. So with Internet of Things, right? Internet of Things. I think this term have been around for, I mean, have been mentioned many times. So basically, Internet of Things is a part of Industrial Revolution 4.0. Okay, 4.0. So uh, what is basically uh, Internet of Things is where the device, okay, can share their connection with each other over the internet. Okay, and so these are basically the interface and communication between system and object devices. Uh, and there are three things very important in Internet of Things. First is the volume. Volume means the number of device can be connected together. Number two is the velocity. Velocity, okay, means that how fast, okay, the device can connect with each other, and most importantly, how data can be transferred from one part of the world to another part of part of the other part of the world. And the third one is veracity. Veracity. Veracity is the what is called as the confirmation of data, or fact. Okay, facts checks. Okay, or validity. Okay, how is data is validated. Okay, so if you think about like to now in the current situation due to the COVID, okay, 19 outbreak. Okay, some country like South Korea, they use the concept of Internet of Things to monitor their citizen. I find it very useful for what has happened in South Korea, and I think maybe it could be done in Malaysia as well. So where during the outbreak, the government, enforce all the citizen to use or install an apps which monitor the activity of the citizen, every citizen. So especially this is very useful, especially for people who are under quarantine. Okay, they are under quarantine. They have to isolate themselves in house, so they can use the apps which install in the computer to check every day. They can check, they can verify where are the user. Okay, and also if the citizen or any citizen who tested positive, so they can check their information. So there's a issue about privacy and security, but in term of the in time, in desperate time, I think the government can use their power, or they use their authority to extract data. So not to spy on the people, but to extract data. For example, someone who got infected. There is a case in South Korea where a person got infected. Okay, and then first the authority asked the person to give information. Okay, information about where did you go, who do you contact, or what have you, where have you been, but the citizen refuse to give cooperation. So what the authority do, they bypass, okay, this the authorization. So they use the system, they log into the citizen account and to phone, and then they check where they have this person go, and then they can do the tracing. So this is much more efficient, okay, in terms of uh, tracking down the activity of the affected person. So that is how internet or concept of internet of thing can be useful in time like the COVID-19 outbreak. Okay. So another thing is that embedded sensor. Okay, embedded sensor is a part of, basically is also a part of Internet of Things. Okay, so embedded sensor, or sometimes called as sensor node, okay, it is a part of a network. Okay, so it is placed in physical world, okay, that interact with the environment or physical parameter. Okay, for example, okay, in many sensor node, it can be used, it can be seen in the agriculture. Okay, agriculture where the sensor node monitor the uh, soil condition, temperature. Okay, monitor the water level, monitor the pH, monitor the weather. Okay, and these embedded sensor or node are often physically small. Okay, they can be made small and can be placed on the surface of skin, for example. Okay, and then they can be disposable. Okay, once you finish using the device, you can just throw it away. So it's very cheap and very efficient. Okay. Okay, and then maybe some of you already using the embedded sensor. Okay, like what you have on your smartphone, a smartwatch. Okay, so where you can measure the heart rate. Okay, and other vital health. Okay, uh, either vital health parameters. Okay, also when you do sport or you go for a jog, so you can monitor your condition and you can monitor your progress. Okay, but the important characteristic is small, okay, and can be embedded, and it can be capable of doing sensing and also actuation, okay, or actuator. It means that this system, okay, not only can sense, is only can administer something. For example, administer drug or administer oxygen, okay, or administer substance. Okay, for example, in agriculture, so there are actuator like pump. Okay, the embedded sensor that integrated with pumps, then so it can be the system can deliver water or water the plants during a certain time or condition. Okay, so these are the embedded the typical architecture of a MEM sensor. So MEM stands for micro electromechanical sensor. Micro electromechanical means that it's very small. Okay, very small in the size of micrometers. Okay, electromechanical means that it can also act as an actuator. Okay, actuator. Okay, rather than a sensor. Okay, so it also is often embedded into a sensor node platform. Okay, and so it is basically a combination of hardware and software system. So you can see this is the basic architecture of a MEM system. Okay. So can step here. I think you can read this by yourself. Okay. So this is an example of interface of embedded sensor. In any embedded sensor, it must at least have a processor. Okay. Like for example, Okay, in this system we have a ATmega processor, and also it has an input output. Okay, input output. Okay. Also, it has memory, RAM, analog to digital converter, and also it must have communication or interface capability. Okay, like UART and serial peripheral interface or SPI. Okay, and also some embedded sensor have the capability to perform wireless connection. So there are the challenges, the main challenges, which can be divided into 3 key areas, which first is the energy consumption. So because this embedded sensor is placed or integrated to a remote places or to a remote object, okay, which connected into the network. So it is very not practical to have a power or wired power source. Okay, so the system must have a capability to have its independent, or have its own power supply in the form of, for example, battery. Okay, and also it has a capability to like operate at an optimum level or optimum performance. Okay, maybe we can add renewable energy option, like for example using a solar, okay, or power cell, okay, and other option like energy harvesting over or using over the Wi-Fi signal. Okay, so that is called an induction energy harvesting. Okay, and sensor operation focus on collaborative signal processing algorithm. Okay, so basically, how do you, if you have a wide sensor connection or you have many sensor nodes, okay, how do you, okay, of course there will be one gateway to the internet, for example, one, okay, one in the middle we have a gateway, okay, or router, okay, router, one router connected to many sensor nodes, okay, many sensor node, S1 for example, S2, okay, and maybe the other sensor is a bit far away, sensor 3, okay. So this is not very efficient to connect one by one, or this is called as the I think it's called as the ring network. Okay, maybe using the algorithm, sensor node 3 can communicate to sensor node 2, and sensor node 2 can transmit to the router. Since sensor node 1 is close to router, there's no need to go through sensor node 2. So that is called as the sensor operation. So using the processing algorithm. Okay. Self-configuration must be so the application and whole must be self-configurating. For example, okay, when the sensor is not, one sensor is not doing any measurement, so it should go to sleep. Okay, should go to sleep to conserve the energy. So when it is required to do to transmit data, so the sensor will wake up. So that is an example, self configuration. Okay, these are the application, for example, in the military. Okay, so like here, this is, you see the gateway nodes, and then there are many sensor nodes connected to the gateway. Okay, this is the example. Okay, example. Okay, the human health monitoring or performance monitoring. Okay, and also in the supply chain. Okay, supply chain of, for example, in the fish farming or in the agriculture or in the garbage truck. Okay, so I think that's the last part of the uh, class for this week. If you have anything to ask, you can ask. So I think if you have nothing to ask, we can stop our session today, and then we will meet again next week, inshallah. Okay. Thank you for participating, and I hope to see you soon again next week. Thank you.